Yeah.
Yeah, thank you, Dr. Rahul. So just to confirm, is my audio clear and everyone is able to see my presentation? So anyone could respond?
Yes.
Okay.
Yes.
Thank you.
Participants, you can see that, right? Yeah. Okay. Thank you, ma'am. Thank you, ma'am.
Okay.
Yeah.
Yes, sir.
So I welcome all of you to this session, which is going to be on computational techniques for complex systems. So as you know, in any workshop, if it is online or offline, the session just after lunch is known to be the ghost session. So I have made the presentation in such a way that it is not too theoretical, not too mathematical, but at the same time, it definitely introduces what is necessary to be introduced, and also considering the varied demographic of the participants, because this is a very unique effort from Dr. Rahul and Dr. Arun to host such a wonderful workshop. So first of all, I would like to thank them for giving this opportunity, and keeping in mind of the target audience, I have made the presentation in such a way that it caters to the different interests, and any of you wish to interact more on it are welcome to do so. I will share my contact details at the end of the talk. And after an initial lecture from my end, my PhD student, Ms. Aishwarya, will be giving a tutorial on some selected techniques that we are discussing here. And after that, we can have whichever way we prefer. Q&A could be before or after that. So let me begin. So first of all, let me try to give a definition, or let me try to explain what is a complex system. So a complex system could be something like a marine ecosystem. So it's a very complex natural system, and it could be even something like climate, and it could be a mammalian neuron, or it could be as complex as we usually say the rocket science, so as complex as a solid rocket motor in engineering system. So many of the systems which are natural or engineering systems, we can model them as complex systems. Now, when we say we can model them as complex systems, what we exactly mean by that? And what does this word complex mean? So the word complex here is not used in a rhetoric sense. So we know that the English word complex, in our usual language, we use it in the usual parlance. We make it like sound like complicated. So here the complex, in the complex system domain, we use it in a very different way. That is, we use it in such a way that like this complex system is something which is, you could see here. So this is just a pictorial representation. I'm sorry, my presentation. One second. I don't know what happened, but let me just to reshare my presentation.
Yeah. Yeah. What happened, sir?
I'm not sure what has happened.
Just reshare it, sir. All right. Thanks.
Yeah. Yeah. So the what you could see here is actually something that is representing the, some of you could understand that this represents the flag of Canada. So this is a pictorial representation of what a complex system is, because you could see that this is from a very aerial view, it appears like the flag. Now, when you go closer and closer, you could see that this is something consisting of different people or different human beings holding a particular color full card, or maybe wearing a particular color, a dress of a particular color. So when you go deep into the system, the subsystems, the units of the system, so if you take each unit of the system, then you cannot see the flag. Whereas if you see the system as a whole, you could see the flag. So it is something like we say the forest and the trees. So that is a very rudimentary definition of complex system. So I will give you a more proper definition is to follow, but just to motivate you. So this complex here is not, I wanted to emphasize that it is not used in the sense it is complicated, but it is used in this particular sense. Now, what are some examples? For example, if you take an ant hill, I know that ant hill, there are different ants, like there are worker ants, there are different, let's say, ants which guard the system, ants which collect the food. And there can be different units which are responsible for different works. Now, the studies in that domain show that even if you are destroying one particular unit, then if you are trying to see what happens, then what happens there in such an anthill is that naturally there is a transition that happens from one unit to the other, and some other assume that duty and they continue. So there is a natural transition that happen in the subsystem. Okay. So now again, you could see something like if you are considering something very complex as a human, say the interaction of human genes or proteins, interaction in a human gene, then you could see again it develops into a system wherein there are a lot of subsystems interacting with each other. And some of the everyday examples could be something like a stock market where you have many people are interacting with each other. You could now see many stock companies are interacting, many human beings are interacting. So again, it could be something like a climate system. Then again, you can see that, or it could be a traffic that is happening in a city. So in a big city, if you want to model the traffic flow in a big city, so what is happening, or it could be even something like your social media networks. That is, all of us have social media handles, social media accounts. So if you try to picturize your social media friendship network, it appears more or less something similar to this. And or you could also see there could be beautiful spatiotemporal patterns that can be there in nature or in engineered systems. So these patterns are also like depicting systems which are complex in nature, so which could be dealt with this complex system theory. That's what I mean. So you can use this as a complex system theory, or using complex system theory you can actually do that. Now, so I have not still given the proper definition of complex system. So now coming to the proper definition, what could be a complex system is, actually it's literally one in which there are multiple interactions between different components. So basically, for you to model something as a complex system, you need to look at three things. One, there are interacting subsystems. There are interacting subsystems. Two, these subsystems are interacting without a master control. That means there is no central control in the system, which is making the system to behave in a particular way. So the second thing is there is no central control. So the first point is there are interacting subsystems. Second point is there is no central control. And the third most important point is, in a complex system, when you view the interaction of the subsystem, you observe certain phenomenon which is called as an emergent phenomenon, which is not a property of the subsystem. That means a best example will be if you take our consciousness. So which is like, since the conference is conducted or the workshop is conducted by the School of AI, so it is apt to discuss about consciousness. So if you take consciousness, now people are thinking about what exactly is consciousness. So you know that our mammalian brain consists of several different neurons. But if you take a single neuron, you cannot attribute this aspect of consciousness to it. Whereas when they are interacting together, there is an emergent property which is like the feeling of self or awareness or consciousness, as we call it. And this is the reason why people are interested to see whether AI systems can be conscious. So because if it is an emergent property, then we could expect such emergent properties from AI systems as well. So to repeat my definition, so a complex system is one in which you have interacting subsystems and it does not have a central control. Third, you have an emergent property. This emergent property need not be, or mostly will not be, the property of the subsystems involved. Now, if you look closely into this more, this interaction between the subsystems will mostly be nonlinear, and these interactions are very interesting for us to analyze. And these interactions, these emergent properties, what are the emergent properties? One example I gave is consciousness. Another emergent property could be, for example, if you are facing a stock market crash, it is an emergent property. So suddenly the entire stock market collapses. And if you take human body as a complex system, onset of a disease is an emergent property. Then if you see a pandemic, then the entire world getting into the grip of the pandemic, the entire world getting affected, that is like something like an emergent property. Or if you see a cylinder shedding vortices, which is placed in fluid flow, the spatiotemporal patterns that it creates is an emergent property. So these are the emergent properties that we are interested in, and most often this modeling or this perspective of applying complex system helps us understand and model systems better. So that is about complex systems. Now, it is not only about that interest, but more than that, these complex systems undergo what is known as critical transitions. So they undergo critical transition. And what we mean by critical transition, we will see in a minute. Some of you may have read this book by Malcolm Gladwell, which says the tipping point. So this is a very famous, this is the terminology now the ecosystem people, and this is a very glamorous buzzword in ecosystem nowadays. And you could see many papers in prestigious journals such as Science, Nature, etc., with this tipping point as the title. Now, the tipping point in general, in a most rudimentary sense, tipping point means how little things can create big difference. That is how there is small change that can happen in the system that could eventually result in a very drastically different qualitative behavior of the system. So we will see some examples. Suppose that this is a very famous author working in this area, Sheffer. So you have a ecosystem, and you have some variable. So you could see now you can relate this. So my request is, whenever I am seeing an example, that example is just an example. So you could relate it to your own field. You can expand this example. So now I will be switching on from a specific example as well as from a generic thing. Both I will be doing. So now if you want to see it is in a very general perspective, you could see that it is a system in which some parameter is changing. You are observing something in the system. So you're changing some parameter and you are observing something in the system. So now let us take this. So if you are here, if you are in this solid black line, that is in the top line, so you are changing some parameter. So you are here. So in this case, this happens to be dryness of the climate. And this your y-axis or the observable, the one which you want to observe, the quantity that you want to observe, that is the mean vegetation. So you are saying that the dryness is very low, the vegetation is there, dryness increases, but still the vegetation is there. You don't see any problem. So it goes all well. And finally, you reach a point where any more increase in dryness, what happens? The system tips, system transits from a fertile ecosystem to a barren ecosystem. Suddenly it's all gone. So what is happening is that this is a critical transition. And this critical transition you can study by modeling your system as a complex system. So that is the point. So now it is something like this. For example, if somebody is, say, smoking 1 cigarette, 2 cigarettes, 3 cigarettes, like that, if they smoke for 1 year, 2 years, 3 years, their health condition is pretty much good. So they say that smoking is injurious to health is a myth. So then what happens? Suddenly, at a particular point, then they start developing symptoms which shows that their body, which is a complex system, has undergone a transition, and the transition that it has undergone is similar to a critical transition. So this is an interesting thing. And it is not only limited to Rahul, could you give me presenter status? Rahul or Arun,
Yes, ma'am.
can you give me?
Yeah.
Yeah.
Yes, sir. Yes, sir. Yeah.
Yeah.
So it's visible, but sometimes it is black side. So in a complex system, tiny perturbation can produce a large transition
yeah,
with a sample
yeah.
figure on the left side.
You can just make me the presenter. I think now I do not have that status. So if you
1
make
minute.
me a presenter, then that will be fine.
Okay, I will device settings, setting options. Yeah, 1 minute, sir. It's in meeting options, right, sir?
Yeah. In meeting options, you could just, or you can just click on my name, right click on my name, and then change also. That is also possible.
That is not possible here, I think so.
Oh, okay.
You can present to specific people and present people in my specific people. Choose presenters, yeah.
Yeah.
I'm saving that.
Yeah, fine.
Yeah,
Thank you.
done, sir. Yeah.
Yeah. Now I am a presenter, so I hope I will have. I am just not moving to the screenshot because it is, I think, it will prevent me from seeing the reaction. So that's why I just trying to upload the presentation here.
Yes, sir, please.
Yeah. I'm just reloading it because I lost it in between.
Yeah, it's visible, sir.
Yeah.
Can you scroll it?
Yeah. I will just switch off my video so that there will be no broadcasting issues, like bandwidth will be better. Okay, so now I was explaining about this. So what may happen now is that you are having a tiny perturbation, so that can actually tip your system. So this could be the final straw on the camel's back. So this is not just limited to natural systems and biological systems. It can also happen to an engineering system, and that's what we did. We did in a canonical combustor. We tried this by increasing the energy that is available for the combustor. So then we could see that the combustor turns into an oscillator. That is, the natural modes of the combustor gets excited, and then you develop oscillations, acoustic oscillations in the combustor. So what I'm trying to motivate here is that this critical transitions will be there even in many systems that you are dealing with. So if you are recasting your problem into this complex system terminology or complex system parlance, you could use the entire literature of critical transitions to study about your domain. Now, what are the types of transitions that we will see? So during the introduction, Dr. Rahul was mentioning that my area of interest is catastrophic transitions. So to motivate what is catastrophic transitions, so you could see here that there is a condition and there is a system, and you are changing the conditions of the system. So what is happening is that the system is transiting, and then it is coming to an alternate, sorry, I will use the pointer. So it is coming to an alternate state, another state it is coming. But now you could see that if you are if you are going back, if you are removing what is there in it for like what is responsible for this change, if you are removing it, then, or if you are reverting it, then you will go back to your original system, original state. So these are called as non-catastrophic transitions. Whereas in a catastrophic transition, what happens is that usually, if you see here, you could see two solid black lines separated by a dashed line. So what happens here, when your conditions are changing and when you are reaching this critical transition point or point of critical transition, your system transits to the other alternate state. But now you look at this, even if you change the condition, it will not go back to its original state, which is the top solid black line. It will continue to be there in the bottom line for a while. And you need to really change the conditions in such a way that you have to make it very slow, that it will go back to this. So this is the reason why many of these climate change people, you may be knowing that why they are making a big hue and cry about we in greenhouse gases, we increasing the temperature, etc. Because once we approach a transition, even after that, even if you decide that you want to say stop it and come back, it is very difficult for us to do so. You need to wait. You need to really reduce it in order to go back to your original say state. Now, again, another aspect that could lead to this transition is the noise present in the system. So if your system has noise, then the noise can also transit your system from one stable state to another stable state. So now this is about the complex system. So the complex system, why we are studying complex system. So I gave you first the explanation for complex system. Second, why are we interested in this complex system formalism? It is because the complex system formalism could be used to understand transitions that are happening in systems. Now, how do we further model the system? So we further model the system using what is known as dynamical system theory. So I will very quickly introduce you to dynamical system theory. So suppose that you have a beam, and this beam, you are putting a weight on the beam. So anybody, if they are from mechanical background, they will easily understand what is known as buckling of beam. And even if you are not from the mechanical background, the simple experiment will be, if you have a ruler, a glass ruler or a steel ruler, if you can place the ruler or scale in the upright position, and you apply pressure on the top of the ruler, for initially for low values of pressure it stays straight, but if you apply more pressure, then what happens is that the ruler buckles, the scale buckles. So the weight that you have added, the little weight that you have added extra to make the beam buckle, that is a small change in the system condition. But what has happened to the response of the system? The response of the system has dramatically changed. So for an infinitesimal change in any of the system parameter, if it results in a qualitatively different behavior of the system, we call such a change as a bifurcation. And using this, we can study actually what is happening in a complex system. We can actually study using this bifurcation parallels. For example, you can create mathematical models of your system. So this is first computational technique. So now I am coming back to my title. So the first part of the title was complex, the second part was complex system, the first part was computational technique. So the first computational technique that you could use is using the canonical simple mathematical models to describe your system behavior and to understand the stability aspects of your system. So if you are able to model your system using a equation such as x dot equal to r plus x square. Now r is your system parameter, x is your variable, x is the variable of interest, and you are able to change r. So now what happens if you are little bit, if you are just plotting this for the different values of r, you could understand that if r is negative, then you are going to have two values of x, that is, two values of x for which this x dot will be 0. And if r is equal to 0, there will be one value of x for which x dot will be equal to 0, which is 0 itself. And if r is positive, it is very obvious that x dot will never be 0. Now, what is so great about x dot being 0? X dot being 0 or x dot being say negative or positive, it actually tells about what is happening to your system, what is happening to the rate of the system. So when x dot is 0, that means nothing is changing in the system. That means the system is in the equilibrium state, or the system is in the steady state. So when you are recasting your problem into a mathematical model like this, and if you are able to understand the points where which x dot is going to be 0, those are the points which are equilibrium points or the steady states. These are the points where your system will eventually reach. Now, you know, when you study equilibrium in your undergrad level or even in your +2 level, you must have definitely studied. Equilibriums are of three types. That is, the equilibrium could be a stable equilibrium, it could be an unstable equilibrium, or it could be a neutral equilibrium. And stable equilibrium is one in which even if you perturb the system will remain there. Unstable equilibrium is one in which if you perturb the system will transit from there, and neutral equilibrium is one in which if you perturb it, it will go to the no state and it will stay stable there. So like that here also, I am not going to detailed explanation of this, but I'm just giving you an overview. So here you could see the black dot and white dot. Simply you just imagine this way. X dot, you imagine X dot as a velocity. So if you consider this black dot, this X dot curve is intersecting X axis, which means X dot is 0 at this black dot. Similarly, X dot is intersecting this at the white spot, so that X dot is again 0. So this white spot and black spot represents 2 points where the velocity is 0. So imagine that something is flowing. Just this is again an imagination, a finite model. So when the velocity becomes 0, there will be no flow. That means you are in the steady state. However, if you are increasing your X, so suppose if you are in the black dot, and if you are increasing your X, means you are trying to move towards the right side of the X axis, like you are moving towards this right side. When you are moving like that, what happens to X dot? X dot is always defined by this curve. So when you are moving towards the right, you look at the X dot, and X dot is negative. So from the black dot, if you move towards the right, X dot becomes negative. That means it has a negative velocity. So it pushes your system back to the black spot. Similarly, if you are moving towards the left, then your X dot becomes positive. That means it is a right-sided velocity. So it pushes your system back to the black dot. So what does it mean? So if you are on the black dot, and if you are trying to perturb the system by giving some initial condition plus delta x minus delta x, whatever it could be, even if it is going to the right side, it is going to come back to the black spot. Even if it is going to the left side, it is going to come back to the black spot. And by similar arguments, you could understand that if you are there on the white spot, then what happens is that if you are a tiny perturbation will take you away from the equilibrium state. So this way, using this bifurcation theory, you can study the critical transition that can happen in a complex system. And you can understand the points which are called as stable points and unstable points. Now, I will just, for the want of time, I will skip certain aspects, and then I will go to the one important thing which I wanted to tell, which will help us further navigate. So you take a system, something similar to this. Okay, so something similar to this. If I am taking a system, something similar to this, X dot is equal to Rx plus X cube. This is called as a supercritical transition. And when X dot is equal to Rx plus X cube minus X power 5, it is called as a subcritical transition. So I will explain it further in the other slides. I am sorry for being like I'm not explaining the mathematics behind it, because I know that the time I do not have that much time. So because I want you to get at least some tutorial session as well. So now let me just believe me that if you are not having a dynamical system introduction, believe me that there are two types of transitions that could happen in a complex system. One is a supercritical transition, one is a subcritical transition. And I will tell you why am I interested in telling you both, because depending upon this, so this is the first computational tool that you are going to use. Suppose if you have a model for your system, using that model, you can actually determine the type of transition that will happen in your system, and that type of transition that can happen in your system has an implication on your system dynamics, system stability, etc. So let us see that. So first we will see the supercritical bifurcation. So supercritical bifurcation is, before we begin, I am just to make things more clear again, because some people again join. So x-axis, you have something called as control parameter. So this control parameter could be anything. For example, this control parameter in the case of an ecosystem can be dryness of a climate, rainfall, the global temperature. In case of a human being, if you want to model the human being, that is the amount of sugar intake, or the amount of cigarettes that one person is smoking, or the amount of exercise that one is involved in. It could be something like that. If it is a stock market, it could be the government policy, it could be the geopolitical situation, it could be anything like that. And if it is an engineering system, it could be something like if you are changing a parameter of your engineering system. So if it is a mechanical system, it could be something like if you are putting an airfoil onto on air, like if you want to analyze the wing of an aircraft, then it could be something like the velocity of the air, or it could be something like the Reynolds number if you want to make it as non-dimensional. Now your measure is something that you are interested in, the output or the performance of the system. That is called as the measure. So you have a control parameter and you have a measure. Okay. So now what these blue circles and red circles mean? Blue circles are indicating stable states and red circles are indicating unstable states. So we just now, in the 2 slides before, I explained to you, there could be stable states and there could be unstable states. So stable states are those, if you are perturbed from those states, you will come back to those. And unstable states are the ones in which if you are perturbed, you will go away from them. So have that in mind. So the blue ones are representing the stable ones. The red one is representing the unstable one. Now, let us take this example. So we are going further. So what is happening is that if you are increasing the control parameter, if you are having a supercritical transition in your system, and if you are increasing the control parameter, everything is well and good until you approach this point. And after that, what happens? Slowly, your system behavior is slowly changing. So suppose that you do not want, this could be even onset of oscillations. So many systems undergo onset of oscillations. So this could be like, so for example, if you take a power grid, so your power grid is stable till you are adjusting, you are adding some renewable energy. So up to a point of renewable energy, your power grid is stable. There are no oscillations. But suddenly, any more addition, a slight addition, what happens is that your power grid becomes unstable and you have oscillations in the power grid. So this could be something like that. So this is an oscillation. Now you understand that there is an oscillation. So what you do is that you reverse it. You reverse it and you come back to your original state. So this is a very safe thing. So this is a system that which you can control very nicely. But now suppose that you have a subcritical transition. So in the subcritical transition, what happens? You again go to the same point where everything is, the story remains the same up to this point for the subcritical transition. But now you see, if you hit this transition point, in case of a subcritical system, there is a very big change in the response. Suddenly, you are just lost to something that is of very high amplitude oscillations may start in your system. And unfortunately, most of the systems which undergo instability, they will all undergo the subcritical transition. And more than that, what happens is that to add trouble or pain to the trouble, if you are reversing the condition, you may not come back to the stable non-oscillatory state. You may have to still go back and you have to really reduce your control parameter to come back to this. So in a subcritical state, you have actually 3 different regions are there. One region wherein you are stable and another region wherein you are actually unstable in the sense engineering system, like you are on the top of this. And in this middle box, you could see that you have 2 stable states separated by an unstable state. And this we call it as a bistable state or a bistable system. So if you are working with data science, if you are working with mathematical modeling, then you can understand that, or I encourage you to explore the literature on bistable systems, because many practical systems we could model them as bistable systems. And now what is so interesting about these systems, you understood this in the most interesting thing is, once you enter into the transition point, you cannot come back that easily. So one example that my advisor used to give is that this is like dealing with your friend and your girlfriend. So the supercritical transition is something like you are dealing with your friend. So having some, like your relationship is all smooth. So suddenly you develop some kind of trouble. No problem, you take your friend to canteen. So then everything is settled, or you take your friend to maybe to a treat. So everything is settled. Whereas when the subcritical transition, what happens is something like that, you are dealing with your girlfriend or boyfriend. So what happens is that if there is an issue, then you may have to buy a lot of costly gifts. You may have to wait for 1 or 2 weeks or more than that. So since I am not that experienced in that, so I actually reframed the example. And the example that I used to tell, especially if there are students, PhD students are here, or PhD guides are here, supercritical transition is something like dealing with your lab mates, and subcritical transition is something like dealing with your advisor. So like if you meddle with your advisor, then getting him back to a good mode is really, really difficult. Now, so the most interesting part here is the bistable region. So this is called the catastrophic transition, and our aim is to develop early warning signals for this catastrophic transition. Okay, so in the bistable region, why we are interested in developing? Because in the bistable region, your stability of the system is dependent on initial conditions. So if your initial conditions are below the unstable state, you will come back to the stable non-oscillatory state, and if it is above that, you will always end up in the undesirable state here. So one more thing just to clarify, in engineering sense and in physics sense, there are two things. Unstable means it could be two things. For example, if you take a bridge which is not oscillating, so the engineer says it is stable. Physicist also says it is stable. Both of them agree there. But now imagine that because of some wind is there, wind speed is increasing, bridge started oscillating. Now the engineer will say the bridge is unstable, but the physicist will say still the bridge is stable because it is in the stable oscillatory state. Okay, so please understand the difference between stability. When we talk about stable equilibrium, for an engineer, it could be an unstable state from the utility perspective. For example, a power grid which has completely failed and blackout has happened, it is actually a stable state, but it is an undesirable state for engineer, for the end user. So if somebody develops a disease, for a physicist, for a mathematician, mathematical model, it is again a stable state. Disease is a stable state. You are staying there. You are in that state. But for a physician and for the patient, it is an undesirable state. Okay. So our aim is to develop, say, warning signals for this. But before that, before we venture into that, what we need to understand is, suppose that if you do not have, so the first computational technique is you create a mathematical model and you do what is known as bifurcation analysis. So by bifurcation analysis, you could understand the nature of transition that will happen in your system. Now, the second thing is that suppose you do not have a mathematical model, how will you proceed? You only have data. So if you are dealing with data, if you are only have observation, suppose that if you are taking vibratory signals from a machinery, so you are doing online condition monitoring, so you are taking signals from a machine. So now you don't have any model. You don't know how the model of the machine will be. Either it is too complex for you to make it, or you do not have direct access to it. So what will you do? So then there is a very beautiful theory that is known as Taken's embedding theorem. And based on the Taken's embedding theorem, there is a very nice computational technique which is known as phase space reconstruction. So before I explain that, let me just very quickly explain what is a phase space. So phase space is very simple to understand. All of us know the simple harmonic oscillator. So the simple harmonic oscillator, if you are plotting the time series of the simple harmonic oscillator, you know that it will be either a sine wave or cosine wave like solution will be there. Now, if you take, if you are plotting your velocity with respect to time or your position with respect to time, that is what it is giving you, either a cosine or a sine wave. Now, instead of that, if you are plotting a single harmonic oscillator state in a space which is created by velocity and displacement as its variable, suppose x-axis is displacement, y-axis is velocity, then that is a different space. So I am not representing the system in an xt space. I am representing the system in an x dot space. Then what happens? The simple harmonic oscillator will look like a circle. Always the simple harmonic oscillator state will be in the periphery of the circle. So that space which we create, the imaginary space which we create by means of state space variables, we call that as the phase space. So you can create this when you know all the state space variables. But the problem is, when you do not have access to the mathematical model and you have only experimental data, and mostly we do not have sensors to measure all the state space variables. Suppose if you have a very complex engineering system, you may have to measure too many variables, but you don't have access to too many variables. Either you don't have access or you don't have provision. You're not rich enough to employ that many sensors. What will you do? You can measure only one. Suppose that you can measure only one variable. So can you create the phase space? Can you get an idea about other variables? The answer is yes, you can get, and that is what known as phase space reconstruction. And how will we do phase space reconstruction? So Ms. Aishwarya will tell it in detail in terms of tutorial, because why I avoided a tutorial as we proceed is that I want to cover more things. So I just want you to get exposed to certain tools so you could explore it further. So if you are interested, and I will be very much interested to interact even after this, if any of you are interested. So now, in order to create this phase space from a single, say, your observation, a single observation, you want to create your phase space, what you should do is that you are calculating two parameters. One is known as the optimum time delay. So basically, the idea here is, if you are observing a single variable and if you are creating delayed variables from this variable, that means if you are observing x of t, and now if you are able to create other variables like x of t plus tau, or x of t minus tau, x of t minus 2 tau, etc., then these variables actually will represent the system. So again, I will explain very easily for you. Now, if you are observing velocity, or if you are observing displacement of the simple harmonic oscillator, you know that it is going like a sine. Now, the velocity, which is the other variable, it goes like a cosine. That's the differential of this. Now, what is the phase difference between these two? Actually, if I have a sine wave, I can create a cosine wave if I just delay it. Are you able to understand? I hope you are able to appreciate. That is, if I have one data, I can just, by creating a delay, that is by shifting, by introducing a delay, the other data is embedded in this data. So that is the idea of optimum time delay. Now, by what amount I should delay, that I am determining by what is known as optimum time delay. Second, how many such variables I should create, that is determined by what is known as false nearest neighbors. So, or otherwise it is known as the minimum embedding dimension. So using these two concepts, you can actually recreate the phase space. So what you do here is that, so here is the famous example of what is known as a Lorentz attractor. So you know that there is, if you are interested in, like, if you have, definitely you have heard of this butterfly effect or Lorentz butterfly. So this Lorentz butterfly or butterfly effect is related to an area in which you have three ordinary nonlinear differential equations, and these differential equations, when you are plotting them in the phase space of x, y, z, you get a butterfly like shape. But instead of this access to this x, y, z, if you have access only to one of those variables, either x, y, or z, can you recreate the phase space? The answer is yes. Using this particular computational technique, you can recreate the phase space, and the recreated phase space is topologically equivalent to the original phase space. Now, so we saw, just again to get you back on track, we saw what is a complex system, why do we study complex system, and how do we model complex system. And if you do not have the model, if you only have data, can we do something for the complex system? That all we have seen. Now we are asking the important question, can I be forewarned about the transitions that happen in a complex system? So you saw the critical transition that could happen in a complex system. Can we be forewarned? The answer is yes, because there is a phenomenon called critical slowing down that will precede any critical transition. So this is a very pictorial representation of that phenomenon. Suppose that you have this potential, say, representation of your potential. Okay, this is the pictorial representation of your potential. So you have two wells. So you have two wells, and some changes are happening. So what happens is that because of the change, one well becomes unstable, that means its depth becomes reduced in the picture, in the graphical way, and the other well becomes stable. So the ball which was here in this well, right well, goes to the left well. So that is your transition. So understand that. Okay. So what happens? The ball in the right well goes to the left well. That is the transition. Now how it goes? Your potential is actually changing. So the depth of the potential, the right well is reducing and that of the left well is increasing, and then it goes off. Now, what we mean by critical slowing down? Let us now focus on that question. So now you take the right well. If the ball is in the right well, and if you are far away from the transition, then the right well, remember that if you are far away from the transition, right well has very high depth. So when you are moving a ball which is in a well which is like really, really deep, if you perturb the ball will immediately go back to the center. Okay, so if it is the depth of the well is really high, then the ball will move back to the center very easily. Now the perturbation will die down fast. But whereas as the depth of the well is reducing, that means you are approaching a transition. So in terms of states, one state becomes less and less stable. So you are approaching the transition. Then what happens is that even the small perturbation that you give to the system, it takes a long time to settle down, which we call by the name critical slowing down. Okay, so now this critical slowing down will result in decrease in the return rate. So return rate means the rate at which the system returns to its original thing after a perturbation is given. So if you are giving a perturbation, how fast the system comes back, that is known as return rate. So now there will be a reduction in the return rate and there will be an increase in autocorrelation. So the autocorrelation increases because here now what we are doing is that you are perturbing the system and the system is not going to come back easily. So T, the system observed at T, system observed at T plus delta T, T plus 2 delta T, etc., are looking more and more similar. So if your states are more and more similar, your autocorrelation will be high. So there is an increase in autocorrelation and there is an increase in variance because your fluctuations are not dying down fast. So because the fluctuations are not dying down fast, your variance also increases. So critical slowing down typically results in decrease in the return rate, increase in the autocorrelation, and increase in the variance. Now, if you want to mathematically model this, actually what happens is that your original system is a multidimensional system. So it could be multidimensional and it can have any number of variables in it. And that is represented in general by an equation xi dot is equal to some nonlinear function of x1 to xn plus some noise component. However, when you are approaching a transition, what happens is that there are some dominant eigenvalues and these dominant eigenvalues enslave the other ones. So which is known as, which was first described by a German scientist Haken. And then you become, now your entire dynamics happens in a particular mode. Entire dynamics happens in a particular mode and you could represent it as a single ODE. That is the reason why some of you might be wondering why I told, when I was telling about the mathematical model, I was actually showing you an ODE. Okay, so that ODE is there because a single dimension could represent the dynamics of the entire system when you are approaching the transition. So then when you do, I am not going to go through the entire derivation. So when you do this, say, entire calculation, then you could determine that the autocorrelation of this system is something like e power lambda t. So now all of you who have some exposure to control theory know that a system will go from stable state to unstable state. That is stable, whatever we say stable, that is all disturbances are decaying, to a state where disturbances are growing. That means the eigenvalue is moving from the left half plane to the right half plane. That all of us know. Now, when the eigenvalue is moving from the left half plane to the right half plane, what happens is that there could be non-zero imaginary parts. The imaginary part of the eigenvalue could be non-zero, which may result in oscillation. Now, the real part is actually the envelope. Now, when it moves from the LHP to RHP, the real part is actually going to become zero. That means in this e power lambda t, the real part of the eigenvalue will approach 0. That means your e power lambda t will approach closer to e power 0t or e power 0. That means your autocorrelation will almost become 1. So this is the reason why your autocorrelation is increasing. By similar arguments, your variance can be proved as sigma square by 1 over sigma square over 1 minus beta square. And when your beta is approaching this, your variance also starts increasing. That is the idea. Okay. So this is the mathematical explanation why the variance and autocorrelation are increasing. And now you could actually record a data. You could actually record a time series. And in the time series, if you are calculating this autocorrelation and variance of the time series before transition, if you start calculating, then you can see here that actually, look at this picture, the original transition is happening at a point F1. But you look at these bottom panels, which shows the autocorrelation and variance, you could see an increase in autocorrelation and variance much before this transition. So using this, you can actually predict the transitions that may occur in your system. So your system could be anything. So if you are able to say get data from your system, and if your system undergoes a transition, then you can predict the transition that happen in your system using this particular methodology. And this we have done again in an engineering system. Again, a canonical combustor, we have done that, and we proved that for a canonical combustor also, this was first study in the engineering system using these early warning signals based on critical slowing down. We did that, and further we extended this study to power grid. So the models of power grid, we again proved that it is possible, and again in stock also we did the same kind of study and we proved that it is possible. So you could see all this in the publications. Now another important aspect here when we talk about transition is, I told you that there could be transitions which can happen because of noise. Okay, but apart from noise, apart from change in the parameter, rate at which you change the parameter, this also could create transition. So this is also very, very important. That is in the sense that sometimes what happens is that the rate at which you change something, that can also create actually a transition, and that is known as the rate dependent transition. That is known as the rate dependent transition. So it is like this. For example, as I told you, the earlier example I was telling you. So if somebody eats one sweet a day, then every day if that person is eating sweet, definitely after a while the person will get diabetes, or high chance that the person may get a diabetes, because if the person is prone to get diabetes, he is or she is going to get the diabetes. But imagine a situation in which the person is not eating just one sweet per day. Since he is okay with one sweet per day, he increased it into 2 sweets per day. Then he increased into 3 sweets per day. He increased it into 4 sweets per day. Like that, if he is increasing, then you could easily guess that when he reaches a critical threshold, what may happen is that even when his system is not really getting into a diabetes state, before that itself, his health will be hampered, right? So the amount, the rate at which you are introducing the change, that itself could create a change in the system. So now, again, I am not going through the entire details of this. This is called as R tipping, and this was first introduced by Ashwin, who is the professor in University of Exeter. So he is the one who proposed it. Later, we wanted to try it out in one of the complex systems, both in numerical as well as in experimental model. We tried this and we proved that this R tipping is possible, and we published this data. So I will just take you to that. So now suppose that if there is a stable state which is represented by this circle, and this blue dot is another stable state. So if you are, and there is an unstable state which is separating them. Okay, so now if your initial condition is this black dot, and usually you are supposed to come to this blue dot, because there is no problem, because your initial condition is less than this, you cannot cross this unstable state, so you will come back to the stable state that is available. So you are reaching here. Now another possibility is, what happens is that the circle shifts. If the red circle is shifting because of some changes that happen in the system, if the red circle is shifting, then what happens? Remember, we are not changing the parameter. For the same parameter, the system on the left is stable and the system on the right is unstable. So for the same parameter, you will get two different behaviors just because the rate at which the system is changed. Okay. So now we worked out another way of introducing this R-tipping, which is known as the preconditioned R-tipping, in which what we did is that what happens if the radius of this red circle is reduced at a rate higher than the rate at which the trajectory is decaying. So then also we were able to achieve this R-tipping, so which is known as the rate dependent tipping. So now this is the pictorial representation of that. So this is a bistable system. So the mathematical model of the bistable system. So now you can see that if there is an initial condition like this here, usually you are expecting this initial condition to decay down. Now, if the initial condition will decay down only when you can see here that there is a rate at which the parameter is changing. And I would like to emphasize that all your engineering systems are rate dependent systems. They are otherwise known as non-autonomous systems. There is an explicit time dependence for all engineering systems. Suppose if you take any engineering system, you are not changing the parameter quasi-statically, you are changing the parameter as a function of time. So whenever you are changing the parameter as a function of time, then the rate at which you are changing that rate becomes important. So you can see here that the red trajectory, which takes the system to a stable state, it is happening at a lower rate, and the green one, which is happening at a higher rate, it takes to an unstable state. Now, I was telling you about the early warning signals that we have developed and whether these early warning signals will be useful in predicting these rate dependent transitions. So we did this in a canonical power system model, and we found that the efficacy of early warning systems, early warning signals based on critical slowing down is very low in predicting this rate dependent transitions. So here your ML or DL comes into your rescue, and we also used the CNN LSTM architecture, and we were able to achieve accuracies as high as 99%. So this is one area that is emerging. So those young researchers who are here and researchers who want to enter into data-driven modeling could start thinking about using AI-based, ML-based, DL-based early warning signals for systems which are prone to instability. And now this is not something that is very theoretical. So this happens like there is a phenomenon called peatland fire. This happens because of this rate dependent transition. And again, the rate at which our temperature is raising, that could actually bring us or make us, because many of you must be knowing that Sahara was a very fertile ecosystem years ago, and it became an arid ecosystem because of this transition. So that is the reason why people say that the rate at which the temperature is rising now, that is actually an alarming rate. And if it crosses a threshold, then actually you are going to face a catastrophic transition and you will transit into a no return state. Now, going back to that's the final tool that I will be presenting is what is known as complex networks. So complex networks are basically, so now we know that complex system is something that is consisting of interacting subunits, and these subunits actually interact in a nonlinear fashion, which will result in what is known as self-organization or emergence. So now you can have various examples of that. So there could be, for example, you can have various people are here. So they are, for example, completely there could be random arrangement, which is like a crowd. So now the crowd, if you are putting a master, which is not a complex system. So if you are putting a force field, then the crowd may arrange now into an organized thing. What is not something like an army. Now, if there is no master, but if there is some emergent properties happening, then the crowd itself may form another pattern that is known as the complex system. That is our society. So society, there is no central master who is creating this. So now such systems can be analyzed by what is known as complex networks. And these complex networks there was a very famous war in Iraq that happened some 20-30 years ago. So there they actually captured the mastermind Saddam Hussein by applying the network theory. So network theory helped the US Army in detecting the central person. That is, you analyze the people and then you arrive at there. And again, the network theory could be used, for example, to understand something like a blackout phenomena that happen in power grids. You can use network theory. And there are many books which talk about this network theory or network science. So I recommend you to read these things if you are having time. So these are very, like, there's a famous statement, 6 degrees. That means your distance between anybody in the world is like just 6 degrees. And if you are a scientist, you will be, or if you are publishing, you will definitely be knowing what is known as an Erdos number. So you can actually check what is your Erdos number. So that actually shows your degree separation from the very famous scientist Erdos, Paul Erdos. So what is the separation between you and him? And that shows the Erdos number. And if the number is less, that means you are writing papers with very James, like your very slow means you are very close. That is the idea. So now coming to this phenomenon of, or coming to this model of complex network, it all started with Euler. So Euler wanted to solve a problem. So I am not going to the details of the problem, etc. So Euler wanted to solve a problem of bridges. So these bridges, like, there was a condition that the land masses are connected by certain bridges, and you need to start from somewhere and end in the same point without crossing a bridge twice. So that was condition. How do you solve it was the problem. Then Euler completely, like, he made this problem into a graph and solved it like a graph. So these networks are basically like you are converting your existing problem into a graph. So you are identifying what is known as, so this first complex networks in the history. So basically what you do here is that you convert your problem into nodes, and your problem into vertices, and you are building connections. So you can make networks of the data, like protein interaction data. You can create a network. You can create the network of share prices. You can create graphical networks of internet. You can create the mobility network, anything that you can create. And you have to remember that these networks are actually phenomenological models. What we mean by phenomenological model, you are the one who is deciding how to design your network. Suppose that if you are working in a particular problem, just imagine you are working in the a transportation problem. So you are now thinking that the places where you want to go, those places you are considering as nodes, and you are considering the, if there is a vehicle transport possible from one place to the other, you consider that two nodes are connected. If there is no possibility, you consider that these two nodes are separate. So this is one example. And you can even do, like, for example, if you want to model a pandemic, you can use the network theory. So there, maybe you could model each town or each city as a node. And if there is a traffic from one city to the other, you can make it as an edge. So that is another model that you could think of. So in this way, you can come up with any kind of phenomenological model that you want in terms of network. So for example, if you want to do it with an image, so if you want to do an image as a network, again, you can do image as a network. Each pixel or each the suprapixels, you could consider them as nodes, and the suprapixels you could connect using some logic, and that will be the edges. So like that, you can create a network. Okay, you can create a network using some model that you want. Now, what is important is, can we construct, and before I go there are three types of networks. One is called as a random network, another one is called as a small world network, and third one is called as a scale-free network. And people are now mostly interested in the scale-free network, and now I recently heard that the interest in scale-free network is not that high because people are moving out of that. But it is like, these are like models of the systems that you can create. Now, if you have a time series data, can you create a network? So that is one question that many may have. Now, you can create this time series data into a network by converting or by using what is known as the visibility graph. So you are converting the time series into some like this histogram kind of structure. So you are just representing the amplitude. And you are saying that if I are sitting on one of those histograms, and if you're able to see the other histograms, the histograms that you can able to see by sitting on the current histogram, you will connect all of them. And if you cannot see, you will not connect. So this is known as visibility. So by using the visibility condition, you are connecting. So in time series, each data point is considered as a node, and one data point is connected to the other data point depending upon its amplitude. So visibility here means it depends on its amplitude. You are connecting it. So that is known as visibility graph. So you may think that how do we achieve certain things by using this? I will show you some examples wherein you have good success by using this methodology. So now that is visibility algorithm, and you have visibility algorithm with various variety. That is, you can have horizontal visibility, you can have visibility algorithm with thresholding, all that. So I'm not going to the details of that. Now some real applications. So you can see that this was again using the visibility algorithm. Transition that happened in a turbulent combustor was captured. So what we used is what is known as a recurrent say network, which is created from a recurrence plot. So from that we were able to understand the transitions that happen in a combustor. So basically what we do here is that we create a network of the time series of different states, and these networks actually represent some topology. So then the topological changes of these networks are tracked, and by tracking the topological changes of the network, you could predict the transitions that may happen in your system. So this was for a combustor, and then we did the same thing for speech. In speech also we were able to do this. So we were able to show that unvoiced speech at times behaves like a random thing, and at times it is chaotic. So we were able to do that. And again, we were applying this to plant growth from images. We were applying this phenomenon to plant growth to see that how, if you are planting certain everything together, like if you are having a large farmland, if you want to understand how your crop grows, you can again apply this phenomena and then do this. And with this, I conclude. So what we have, in summary, what we have done in total is that three take-home points that I want you to understand is you can model your system as a complex system. You can model what is the use. These complex systems undergo catastrophic transition. So you could study the catastrophic transition possible in your systems. Three, you can use different computational tools such as bifurcation analysis, phase space, reconstruction, early warning toolbox, and complex networks, to name a few, because you have more than this, like multifractal, surrogate, then the various other things like entropy, etc. you have. So I'm not referring to all that. So you could use these computational tools to observe the transitions that happen. And the future, what is the future of this complex system research, is that many of these AIML techniques are now being used to understand the dynamics, and many are employing the data-driven modeling techniques, because you have data and then can you arrive at the model. Many of them are doing that. And again, you can also use this complex system theory to understand the working of neural networks. How in a deep learning network, how the network is learning something. So you know that the network actually, that could be many attempts are made in order to understand that as a cell or problem of self-organization or emergence, because these neurons are individual units, and these neurons are now interacting each other in a nonlinear fashion, and now the learning is an emergent property. So that is also another perspective that you could bring. So with this, I close my presentation, and I request if Ms. Aishwarya is here, she could start the tutorial, or if the question answers need to be done now, we can do it, and then you can go to tutorial. So I leave it to Rahul to decide on whichever order that you wish to prefer.
Sir, we can go ahead for the QA first, and
Okay,
then we
fine.
can go for tutorial.
Okay.
Yeah. So is there any queries from the audience? You can write in chat box, or otherwise you just unmute and ask. Is there any questions? Yes, sir. There is a question is from Navani. Sir, if the system
Yeah.
has very short time to respond, will these methods will work?
Yeah, that is again, that is the point of this rate. So you have a critical rate. So what may happen is that if the critical rate is depending upon your system conditions, and the system, whenever you talk about the system's response time related to this, means you are making, that is, you are indirectly, it is like saying that the system is not non-autonomous and the system is rate dependent. Now, such a rate dependent system, the traditional methods, in my experience, will not work, and although it is not effective at least, so we have to use some of these DL based techniques in order to reveal the dynamics of such systems.
Thank you, sir. Is there any other queries? So we can move with the tutorial, I think so.
Yeah.
Yeah.
So,
Sir, I'm audible?
Yeah, audible.
yes.
Please. Yeah.
I'm unable to write it on the chat. Thank you, sir. My name is Pradesh. I just have one question. You said you'll give an example about that visibility.
Yeah.
Can you give one small example?
Of a visibility algorithm? Are you
Sir,
asking
you
for a...
talked about visibility graph where we can actually have an amplitude, and based on this line of
Okay. So, for
just
example,
small
let
example,
us...
something.
Yeah. For example, if you are observing some, say that you are observing an oscillation. So if you are recording that, so you know that at every time the oscillatory amplitude you are recording, that's how you are making the time series. Suppose that initially the oscillatory amplitude is A1, A2, A3, like that up to AN you are observing. So now you are making, what you are doing when converting this into a network is you have made all these A's into nodes. So all A's are nodes now. And now whether the first node is connected to the second node is dependent upon the condition that you are putting forth, which is visibility in this case. So what you are doing is that this A1, A2, A3, suppose that if you are converting them into histograms, and if you are standing on A1, if you are able to see A2, then you will connect A2. So when will it happen? If A1 and A2 are immediate neighbors, irrespective of A2's height, that is A2's magnitude, this will happen. Suppose A1 and A3 you want to connect. If A1 and A3 have to be connected, then A2 has to be such that A1, by standing on A1, you should be able to see A3. But if A2 is such that you cannot see that, then there will be no connection between A1 and A3. So like that, you make connections between the nodes. So what it indirectly means is that if there is a very high amplitude point, that point will be pretty much connected to everything else if you are using a visibility algorithm. Are you able to understand?
Sir, understood. But my question is, what if it is also dependent on how close the neighboring nodes are? What if one is far off, and because of that, it is it's able to get into, it is not able to have the line of sight. But if it is closer to the taller node, it will be actually in line of sight. So isn't
Correct.
it
That is correct.
kind of, so
Correct.
it's all dependent on how we actually arrange the nodes, right?
Yes, that's what I said. So in this case of time series, you are just observing, you are making observations, right? X1, X2, X3. So you are actually making X1, that is the amplitude at T1, T1 plus delta T, it is X2. So the subsequent values you are taking and you are arranging as such. So you are just observing the time series and you are arranging these points as such. So you are not changing the arrangement per se. That is in the sense that your arrangement is fixed in the case of a time series, because it is the way in which you are observing, and in that way you are putting forth this visibility condition.
So understood. Thank you very much.
Yeah.
Thank you, Pradesh. Is there any other queries from the audience? Sir, I think we can move on to
Yeah.
the tutorial.
Yeah. Aishwarya, if you are here, we could start the tutorial.
Dr. Rahul, I don't have the option to share my screen.
Yeah, Aishwarya came. Yeah, I will check. Yeah, wait, please hold.
Sure.
So I will just stop sharing this.
Thank you. So, good afternoon, everyone.
Now
Yeah,
we can share, I think so.
I'm
Yeah.
able to share. Yeah, thank
Yeah.
you. So I will be giving you a brief tutorial on the computational techniques for complex systems. We'll start with the idea of the phase space. The phase space is a representation that allows us to find the state of the system at any given point in time. And to illustrate how the phase space looks, we'll be looking at the Lorentz system, which is represented by 3 different equations. And the variables that we are using is also listed on the screen. I'll be using MATLAB for that. So the equations on the slide will be coded over here in MATLAB. Your x dot, y dot, z dot are dx1, dx2, and dx3 over here. The attractors equations are listed over here. And over here, we will be solving these equations using a ODE solver and then plotting them in 3-dimensional space. So this is your Lorentz, the phase space of the Lorentz system. Now, coming to the tool that Sir was talking about, suppose that you don't have the entire, all the equations of the system dynamics, but you have just one measurement that gives you, let's say, maybe the pressure of a system, but there is a humidity or precipitation value or some other systems that are involved in giving the complete dynamics of the system. How do we go from just having one observation to revealing the dynamics of the entire system? And here we get the tool called phase space reconstruction, where through the Taken's embedding theorem, we create a topologically equivalent phase space. For this, we need two particular parameters. One is the delay vector, which is calculated using a method called average mutual information. And the other thing is called the embedding dimension, which can be either using the false nearest neighbor method or a modification of the false nearest method, which is Cow's method. So in the first time delay embedding method, what we do is we try to find the optimal delay in our time series such that the correlation between the continuous time series values has a bit of a dip. So at this minimum correlation value, we feel that if we delay it at that value, we can represent the dynamics of the subsequent state parameters. However, if you take a very long time series, we will just get uncorrelated features. And in the case of the embedding dimension, it is that dimension where if, let's say, I have 2 points and the distance between these points remains the same even when it is projected to a higher dimension, that will be taken as your minimum embedding dimension. A good example would be, let's say you're looking at a square in 2 dimension, but when I try to project it into a 3 dimension, suddenly the square becomes a cube, which means that if I project the cube onto a 2-dimensional space, I will just be looking at a square. And if I have a cube, which is in fact a cube, but I try to project it into a 4-dimensional space, the distance between the points in the cube will stay the same. And this sort of a method where they try to find the difference in the distance between the points is what is used to get the embedding dimension. So for that, what we do is, using our Lorentz system, we will be taking just one of the 3 time series that is involved in the Lorentz system. I'll be normalizing the data first, and then we will run the average mutual information calculating algorithm. So after running this, we see that this is the first minima at 11. So we see that if we delay our time series by 11 seconds, at 11-second intervals, if I take my subsequent time delayed vectors, I can use that to represent the additional state vectors that will represent the complete dynamics of the system. This is the function of the average mutual information. Similarly, for the minimum embedding dimension, we are calculating up to 10. Let us check whether up to 10 dimensions we are able to get a value. So we see that at 3, because it's a known system, we know that Lorentz system is a 3-dimensional system. After 3, we see that there isn't much variation, which leads us to conclude that the system must be 3-dimensional. So getting these two values, we input it over here. The tau will be 11, and then the embedding dimension will be 3. We create delay vectors, and then we recreate the phase space using this delay embedded vectors. So this is the reconstructed phase space, which we say is topologically equivalent to the phase space that is created when using the differential equations of the system. Now, apart from this, the equations that I've shown above, which uses the AMI and the Cowes method, there is MATLAB currently also has a inbuilt system that you can use, which is called the phase space reconstruction. You can use this function. So the same data, if I run that, it shows that I can take the lag at 10 over here, and then I can take that the minimum dimension is 3. So using this, I can run the reconstruction of the phase space. So this is the reconstruction of the phase space using the inbuilt mathematical model, inbuilt function in MATLAB. So I'll just turn this so that we can see the butterfly diagram over here. So this is one of the techniques that was discussed, where if you have a single observation from a mechanical system or a natural system, you can reconstruct the phase space of the system and thus try to understand the dynamics of the system and identify the state of the system at any given point of time. Another point that was illustrated was early warning signals, where given that you have a time series, can you find out if there are any critical slowing down factors that arises in your system, which will give you any clue so that you can maybe forecast that there is a transition that is impending. For this, I'll be showing you how you can use the EWS toolbox in R. So in R Studio, first I'll be loading the library called TSA, which is time series analysis, which is one of the basic libraries when you're dealing with time series. Here, I have saved the time series that I'm using in a CSV file, which I'll be reading into this function EW1. And then we will be plotting the time series. So this is the time series that we have. This is not the same as the Lorentz system. It's a completely arbitrary time series that I've taken over here. And to this time series, you will need to install a library called early warnings. And when you do that, you can call this generic EWS as the function within the early warning library, which will give you these results. So if you look at these results, you can see that the ACF, the autocorrelation function over here, that increases somewhere between 800 and 1000 seconds. This value increases, showing that and again, you can also check the coefficient of variance. You can check the standard deviation. All of these values show an increasing trend, which means that somewhere around 850 to 900 seconds, the system will be undergoing a transition. So this is a very, very simple and straightforward toolbox that you can, just try out. In case you need some help, you can just go to install in R and you can type in early warnings. So this should get you the complete package. And then you can also try and check whether your deep learning systems are also able to give you a similar result, and whether the deep learning systems are able to give you a forecasting, whether they are able to forecast or predict the oncoming transition before your EWS toolbox does. So with that, I will be going on to the last part, which is your complex networks. So here, with respect to complex networks, I'm coming back to MATLAB for this, though we will be using another software called Gephi for the graph visualization. So though I'll be starting off with MATLAB, you can also look at Python and R as packages for your MATLAB. I mean, for the network construction. In R, it is the iGraph package. In Python, there are so many different networks. Specifically for nonlinear dynamics, you have the PyUnicorn and the NetworkX packages, which have really good code support. And for the graph visualization, again, I'm going to be using the Gephi software. However, you can also look at alternates in Python or in R. So here, this will be the same matrix that we used over here. The same time series is what we're using over here. I'm reading the signal. Because we'll be demonstrating the visibility graphs first, I will be finding the peak of each of these nodes over here so that we can create the histogram. So here I'm reading the visibility algorithm. And then I'll be writing that. Okay, so after reading the visibility algorithm, I'm going to be writing the adjacency matrix that is derived from the graph into a CSV file. So that is over here. Let me also generate two other graphs from two different complex network forming algorithms, the horizontal visibility algorithm and the group thresholding algorithm. Okay. Apart from the visibility algorithms and the group thresholding algorithm, we have one more algorithm called the recurrence. I mean, we have one more method that we can use called the recurrence network. So the recurrence network is based on the system dynamics directly, where we will be looking at the phase space of the system, and we'll be looking at perhaps I can go back to the Lorentz equations over here. Okay. Just assume that we are looking at this particular point in the phase space. And I'm saying that at some particular time, the phase space is over here. I will be trying to measure how many times the phase space is going to come back to this particular region where I have drawn the box. And this, in essence, will give us a property of recurrence, which means, okay, which signifies how often the phase space of the system visits this neighborhood in the phase space. I hope that's clear. Using this concept, we will be creating something called the recurrence network. So the problem of temporal association or the lack of visibility will be solved by this, where we use the actual dynamics through the reconstructed phase space in order to get the recurrence plot and thereby the recurrence network. So from our very first thing, what we do is using the same data, we reconstruct the phase space using the inbuilt MATLAB function, and then we use then we plot the recurrence plot of the network. And from the recurrence plot, we try to get the recurrence matrix, the adjacency matrix for the. So this is the recurrence plot. The dynamics of the recurrence, this is your reconstructed phase space of the system from the inbuilt MATLAB function. And from this plot, from the phase space, we get the recurrence plot. And after removing the self connections along the diagonals, we get the adjacency matrix. So this adjacency matrix also I have saved over here as BREC. If you have any adjacency matrix that you would like to represent, you can go for Gephi. I'll just show the complete process over here. So you go to File, New Project, Import Spreadsheet. Okay. So the first file that we saved was pvis for the visibility algorithm. I'll be opening that. I'm importing it as an adjacency list. And give finish. This is okay. So this is the graph that we have. Now, in Jeffy, you will come across a number of layouts that you have. And if you're planning to use Jeffy, a preliminary analysis of which of these layout methods are more suited to your data is advised. So here we will be going with forced at list 2 because we are familiar with the sort of dynamics that we have over here. And I'll be running this algorithm. I'll stop this, the expansion. So that we can look at it a little bigger. Okay, so this is what we get in visibility algorithm. One thing that you can do is you can go to this panel on the left where you can choose ranking with the degree as the option. And if you click apply, the color of the graph based on the degree will be highlighted as such. So similarly, you can also go and check whether you can change the color of the edges based on the weight of the graph. I mean, based on the weight of the edges. So this way you can get a clear-cut distinction between the nodes and the edges and the weight that they carry. So the second, I will let me import the spreadsheet. I'll go to the recurrence directly. Okay. I'm running the layout. Okay, similar to the previous time, let us get the we will just apply green over here to pale. You will have to play around with these settings a bit so that you can get the best representation for your data. Okay. So this is the graph that we have using the recurrence network. On the right side, you have the complex network measures that you can compute, the average degree of the network. Here it is 2.997, the average weighted degree, your network diameter, your graph density, modularity. Let's check clustering coefficient. It's an undirected graph, so any of these parameters that you need for your graph, you can just get it through this GUI. One more technique that most people seem to be using is checking whether there is an inherent difference in the complex network measures of the system, maybe before a transition and after a transition, and whether those can be used to distinguish a system that is in a steady state versus a system in an unsteady state. Yeah, that is it. So that is the end of the short demonstration. Yeah.
Thank you, Vishwa. Thank you so much.
Thank you, Aishwarya. Uh, Yeah, participants, do you have any queries regarding this tutorial session? or you can write in chat box.
If you need me to go back and maybe show something a little bit much slower, that is also fine.
Actually, you can write your mail ID in the chat box. If there is anything.
Yeah, sure.
Participants can contact you. Okay, thank you, Aishwarya. Sir, can you there? Hello, sir, you there?
Yes, Rahul, I am here.
Yeah. Okay, sir. Then we can wind up this session. I think
Yeah,
so.
yeah. Thank you so
Yeah.
much. Thank you once again to you yourself and Arun, and thank you all the participants.
Thank you. Thanks a lot,
And
sir.
thank you,
Thanks.
Aishwarya. Yeah.
Despite your busy schedule itself, you just came and
Yeah.
talked with that, and thank you for that. No?
Thank
Thank
you,
you for
Aishwarya.
Aishwarya too. Thank you. Thank you, participants. We will come back tomorrow with another session. Thank you.